the effect of the magnetic field, is the Hall effect. And what I'm going to discuss is the quantum Hall. But to discuss the quantum Hall effect in graphene, we have to first of all discuss the Hall effect, the classical Hall effect. So the classical Hall effect, as you probably know, just to remind you, it concerned an experiment that was carried out more than 100 years back by Edwin Hall. And in that experiment, what he had was a metal strip of finite extent, and he applied a perpendicular magnetic field to it. And there was also a planar, or there was electric field along the plane. And as the electrons moved along the plane, the Lorentz force caused them to bend towards the sides. If this plane was not of finite extent, then you would get a current in a direction not perpendicular to the motion, not perpendicular. What I mean to say is that you would get current in a direction which is in some direction like this. But what happens is that if you have it of finite extent, the electrons start piling up on one side, and an electric force develops. And when the electric force balances the Lorentz force, this is the electric force component, and this is the Lorentz force component, and when they balance, there's a constant current in the x direction. We call this the x direction. And you can define the current density, and this is what is called the Lorentz field in terms of the velocity of the electrons and the perpendicular magnetic field, and N is the carrier density, Q is the charge, and one can obtain the Hall resistivity from this relation, where you find that the Hall resistivity is linearly related to the magnetic field. So probably all of us are familiar with this very important experiment in physics. And so there's a linear relation between the Hall resistivity and the magnetic field, and this Hall experiment, or the Hall effect, is important in the sense of it helps to characterize different materials. For example, you can determine the density of the charge carriers, as you know, and the sign of the charge carriers by doing a Hall type of measurement. So this was all that was known as far as the Hall effect, which was an important experiment, a landmark experiment in physics, but as far as the Hall effect was concerned, this is all that was known for almost 100 years. For almost 100 years later, in 1980, von Klitzing performed an experiment where something very different came up, and the result was not the same as what Hall had achieved. And to understand the experiment and its relevance to our topic today, first of all we have to consider the system on which that experiment was performed. And the system is a two-dimensional electron gas. And these two-dimensional electron gas can be realized in metal oxide semiconductor structures, MOSFETs, where the two deck is formed at the interface between the metal side and the semiconductor insulator semiconductor interface. There's a triangular well because of band bending, and electrons are confined. So essentially these electrons are essentially two-dimensional. They're confined in a triangular well where they're free in the two-dimensional plane, but they cannot leave the plane. There's a large energy gap for that. And this was basically the structure or the system on which von Klitzing performed experiments. Whereas these two-dimensional electron gases can also be realized in semiconductor heterostructures. Semiconductor heterostructures are if you grow semiconductors, two or more semiconductors on top of each other, you get semiconductor heterostructures, and also you get this triangular well at the interface where electrons can be confined. And what I'm trying to say here is that it's a very important system because it has garnered at least 3 Nobel Prizes, 2 of them for integer or integral quantum Hall effect and fractional quantum Hall effect, and another one for realization of these senses. So it's also important because it serves as a building block for various electronic devices. It's one of the central elements in various transistors. So now we go to von Klitzing's experiment, almost 100 years after Hall's experiment. And when he performed this experiment in the Grenoble High Magnetic Field Laboratory in France. And what he found was something quite surprising. What he found was that the Hall resistivity that we showed earlier, this red curve depicts the Hall resistivity. And as you remember from the first slide, it was linear with respect to the magnetic field. But what you find here is that it shows these plateau-like structures, these plateaus. And not only these plateaus occur, but at the point where these, or in the magnetic field range where these plateaus occur, the longitudinal resistivity, rho XX, becomes negligibly small. So this is very significant in many respects. And one of those is that what another important feature of this experiment was that he found that this rho xy is quantized very precisely. What that means is that this quantum of resistance is h over e squared, and rho xy is an integral or an integer multiple of h over e squared. So this is very precise quantization. So the jump is very precise. When you change the magnetic field, it jumps by a very precise amount, and that precise amount is an integral multiple of this resistance quantum. In fact, it is so precise that it is correct to 1 part in a billion. Even though these experiments have a lot of disorder, whenever you do an experiment like this, there can be all kinds of dopants because of context, different dimensions of the material, and it even doesn't depend on the materials. So it's a very surprising thing that it's a universal result, independent of a lot of parameters that would, in normal circumstances, affect the result. Those do not. And because of its extreme precision, this has become this standard of resistance nowadays. And so, quantized conductivity, Hall conductivity, and almost dissipationless transport. I mean, two things which seem very strange, that you're getting quantized conductance, but at the same time you're getting dissipationless transport in the x direction. Dissipationless transport, I'm saying, because resistivity is negligibly small. So dissipationless transport and extreme quantization shows that there's something very fundamental going on. And for this discovery, von Klitzing, shown here, won the Nobel Prize in 1980. And now, in order to explain this result, we will need quantum mechanics, and quantum mechanics of electrons in a magnetic field. The problem of electrons in a magnetic field was solved by Landau. It's a standard problem in quantum mechanics. If you pick up a quantum mechanics introductory book like Landau, you can see it. You can read a section on electrons in a magnetic field, and what you would find is that the electron in a magnetic field problem can be mapped to the harmonic oscillator problem, and essentially what you have is these eigenvalues, which are the harmonic oscillator eigenvalue, except that you have this cyclotron frequency instead of the harmonic oscillator frequency. Instead of omega harmonic oscillator, you have the cyclotron frequency. And so what it means is that electrons in a magnetic field, remember that once you apply a perpendicular magnetic field, this becomes a essentially two-dimensional problem, because it's not isotropic anymore. The motion along the magnetic field direction, which is perpendicular to the plane, is not affected by the magnetic field. Because free motion is not that direction, but motion on the plane perpendicular to the magnetic field is different. And what happens there is that the electron levels or the energy levels become quantized, and they become discrete energy levels. Each Landau level has one state per flux quantum. That what that means is that these levels are highly degenerate, and the number of levels or the number of energy states per level can also be obtained by dividing total flux by the flux quantum, which is it. So what is happening, in order to understand this result, we have to look at the density of states. And the density of states without a magnetic field is independent of energy in 2 dimensions. But once you apply a magnetic field, you get these delta functions at these different Landau levels, or at different integrals, n is equal to 0, n is equal to 1. But what happens when you include disorder is that these levels would broaden. And this broadening of the level is important, as I illustrate in the next slide. So what you have here is, this is the situation without the magnetic field. Once you apply the magnetic field, these Landau levels, this density of state breaks up into these delta functions like trees. And these are separated by the cyclotron gap, which is h bar omega c. So that means if you increase the magnetic field, the separation between the Landau levels increases, and as well as the degeneracy of the Landau levels, depending on the external flux, that also increases. And once you include disorder, what you have is that these density of states spread out. And important fact is that there are extended states at the unperturbed values, like in the middle of these density of states, they have these extended states. Extended states mean those states that can carry current. And on the edges of each of these density of states, you have localized states. So essentially, the states in this region do not carry current, and they correspond to localized states. So in order to explain this result, if you go back, okay, I can probably explain it here also. So what happens is when you change the magnetic field, these Landau levels spread out, and the separation between the Landau levels increases. And as you sweep the magnetic field across the Fermi energy either falls into the extended states or on the localized states. When it falls into the extended states, there's a jump in the conductivity, and because these extended states are responsible for transport. But when it moves into the localized state region, there's no change in that conductivity. So you have these oscillations, or these plateau type regions. Those plateau type regions are those ranges where the Fermi energy is moving through the localized states. So there's no change in that region. But once it crosses that region, and the Fermi level now falls into the extended state region, you see that it changes. So basically, one can explain this result on the basis of 2 things. The integer quantum Hall effect can be explained on the basis of a non-interacting electron model. I mean, these density of states are for non-interacting electrons. And if you include disorder. So disorder, in a sense, is important to explain in this result. So you need disorder in addition to treating the electrons, 2-dimensional electrons, as free electrons plus disorder, and you can explain the integral quantum Hall effect. So that was the integral quantum Hall effect for a regular conventional electron gas system, or a 2-dimensional electron system, which is conventional. Now we come to this, where we will discuss graphene, and what changes and what differences arise when we discuss graphene in a magnetic. So one essential difference is, I mean, both the Landau level problem for the 2-deck system, as I said earlier, was solved by Landau as an exactly solvable problem, and for the graphene problem also, it is an exactly solvable problem. And you can determine the energy eigenvectors. This I mentioned earlier. This is actually the cyclotron frequency, E B over m, h bar omega c, and these are the Landau levels. It shouldn't be classical particles, it should be conventional particles, and these are for Dirac fermions. So Landau levels for Dirac fermions, what you have here, there are 2 essential differences. One is that you get energy eigenvalues for positive as well as negative values, because you have these electron and hole regions which are coupled together. And in addition, you have this level with zero energy, n is equal to zero level, which you did not have earlier, because the first level had the energy, or the ground state level had the energy half h bar omega c, whereas here you have E is equal to energy is equal to zero. This was that experiment that I mentioned earlier also, performed by Novus Lab, Zhang, etc. earlier, when they were structurizing the graphene sheets. And what they found was important was that they found, you can also look at the conductivity or resistivity, Hall resistivity or Hall conductivity, you can treat it equivalently here. What they found was special was that if you, for the integer quantum Hall effect, you have to have an integral multiple of E squared over H that I mentioned earlier. Here, 4 arises because you have degeneracy because of the pseudospin, sublattice degeneracy, and you also have valley degeneracy. So there is an extra factor of 4, counting both of them. But, and this is an integral multiple of 4E squared over H. But the extra feature that comes in is this half. So that's why it is called half integer or anomalous quantum Hall effect. And this arises because of the contribution of the n is equal to 0 level, because that level has half degeneracy relative to the other levels. And another important fact or interesting fact about the quantum Hall effect in graphene is that the energy gap, that's why h bar omega c, corresponding h bar omega c in graphene is so large that you can even have room temperature quantum Hall effect. For the conventional quantum Hall effect, you have to have temperatures of a few Kelvin. Or for fractional quantum Hall effect, you have to go down to millikelvins. But for quantum Hall effect in graphene, to observe quantum Hall effect in graphene, you can even do the experiment at room temperature. That's why it's sometimes called room temperature quantum Hall effect. So that is also a very important feature of the graphene system. So that's why quantum Hall effect 300K. So this is the density of state comparison of the density of states, disordered Brodmann density of states, where you see for the graphene system, there's a finite density of states at zero energy. And another thing is that these these Landau levels are equally spaced in the conventional system, where they are not equally spaced in the graphene system. That you can also see from the relation for the energy eigenvalues.
So how many number of states you have in the graphene case?
How many?
Number of states.
Degeneracy of states? That depends on the external magnetic flux.
So it's also known, you can calculate.
Whatever the magnetic flux is, you can determine from the external magnetic flux and the number density. Now, after the integral quantum Hall effect was discovered, then Stormer and others did an experiment. That was around 1985-86, and they took a more pure sample and went down to lower temperatures and higher magnetic fields, around magnetic fields of 10 Tesla and above, and temperatures of around millikelvin, and purer samples. What they found was that a new phenomenon, in the sense that instead of the integral quantum Hall effect, they found fractional quantum Hall effect, where the conductivity or the resistivity was a fractional multiple of the quantum. So what I'm saying here is that this turns out to be a very unique thing, and it's very exciting, and has generated a lot of interest since it was discovered, because it cannot be explained on the basis of the free electron model. You have to consider electron correlations, electron-electron interaction in the system, and what you find is that the quasi-particles or the charge carriers in the systems are fractional charge carriers, anions they're called, and they occur in a two-dimensional electron gas in high magnetic fields, pure samples, and it can be classified as a new state of matter with quasi-particle excitations having fractional charge. And fractional quantized Hall effect was discovered by Stromer, Loughlin, discovered by Stromer and Louis and Sui. They did the experiment, whereas Loughlin developed the theory for it. And what you see here is different from the earlier, and this is actually more recent result, because you have a hierarchy of states where you have these plateaus for fractional values also, and you do have these. There are about more than 30 quantum Hall states discovered up till now, and more are probably going to be discovered later. And so what you need is higher magnetic fields, higher quality samples. Quantization is now fractional, and it was explained by Loughlin in 1982 as a collective behavior of quantum fluid, emergent quasi-particles with fractional charge. So I'm mentioning all these because I want to mention that fractional quantum Hall effect was observed in graphene very recently. We already talked about the integral quantum Hall effect, but now we're talking about fractional quantum Hall effect in graphene. And two groups almost very close to each other. One at Rutgers, one at Rutgers, another at Columbia, reported observation of fractional quantum Hall effect in graphene. And I'll just show you the kind of experiment. The Columbia group, what they did was that they had this graphene sheet on a substrate, and then they etched away the substrate, the silicon dioxide substrate. They etched it away, and these are the gold contacts. And when they did this experiment, what they found was that you see, you can change the magnetic field, or you can also look at change the number density. It will do the same thing, because changing the number density would move the Fermi energy, because Fermi energy depends on the number density. So either way, either you can look at it as changing the magnetic field, and that would move the Landau levels across the Fermi level, or you can do is change the Fermi level, and that would move the Fermi level across the Landau. So you can look at it both ways. It's the same phenomenon. So either you look at the changing the number density, that is in other words changing the Fermi energy, or the magnetic field. And what they found was that around 9 Tesla, they started getting these fractional. You see this is the plateau for the mu is equal to 1 level. That is the plateau for the integral value, n is equal to 1. And this is for these are the plateaus for the higher n is equal to 2 level, or sometimes mu is equal to 2 level is called. So these are the plateaus that were observed for them, and they correspond to the integral values. But if you go to a higher magnetic field, what they were able to see was that these plateaus start emerging, and these are the fractional values. And also, you see the same thing happening here. This is at 0.3, and 0.3 corresponds to the 1/3 level. That means that the first Landau level is 1/3 field, and that's the fractional quantum Hall effect level. This A point here, and it is at 14 Tesla at this number density. So they were able to see these plateaus and the fractional Hall plateaus in graphene.
So what determines the value of Q? You said the charge carriers had charge E over Q.
The charge carrier V.
So what determines Q? In a given situation, is Q fixed?
Q of the quasi-particles or the original charges?
You said the quasi-particles carry a charge E divided by Q.
It depends on the filling factor. If the Landau levels is 1/3 filled, then the charge will be 1/3 of the electron charge. If it's 1/5 filled, then it's 1/5 filled, then it's going to be 1/5 of the electronic charge. So the filling of the Landau levels is related to the fraction charge of the quasi-particles.
And how does
one experimentally change the number density?
How does one experimentally?
Change the number density?
By using gate. If you apply a gate, whether positive gate or negative gate, you can deplete that region of charges or apply charges to that region.
So there must be some gate here.
Exactly. In a hall time measurement, you have these gates and contacts. In one of the earlier lectures, I had that figure where you had these contacts, all of those contacts, which showed there are contacts for determining the hall voltages, for the longitudinal voltages, and you also have gates to control the carrier densities. Now, in this part, what I've tried to show in the first part of this lecture is that the conventional Hall effect, the classical Hall effect, and its quantum version for the two-dimensional conventional systems like the electron gas systems, how does that change when you look at graphene under similar conditions? And what we find is that there are some new features that arise in graphene when you consider quantum Hall effect conditions, or consider graphene in the quantum Hall effect, subject graphene to quantum Hall effect conditions. And now what I want to, in this part of the lecture, what I want to mention is that it is also possible to have quantum Hall effect in graphene without applying an external magnet. It seems quite strange because it seems that we've talked all around, up till now we've talked about the magnetic field, and that is needed to see these plateaus and all of these oscillations. But you can do it in graphene by applying strain. What that means is straining the graphene sheet, because it's a two-dimensional sheet and it can very easily be influenced, or mechanical deformation of this sheet can easily be accomplished. So what is, now question is, what is the effect of local strain on the electronic properties? And there's several proposals regarding it, that perhaps one can apply strain on graphene by changing or affecting the substrate. Somehow by changing the substrate, and because graphene to some extent interacts with the substrate, it can lead to strain on the graphene sheet. So there can be, you can put patterns on the substrate on which graphene rests, and that can cause strain on graphene.
Lattice mismatching?
It can be lattice mismatching also, exactly. Or you can have some kind of pattern like a shallow well or something, and it will be different in one region and different in another region. Strain on the graphene lattice, basically what it does is, when we talk about strain, what it does is it affects the hopping amplitude. Remember we talked about, in the first lecture, there was a matrix element HAB, which related to the hopping of the electron from the lattice site A to B. How is that affected by strain, and what is its consequences as far as transport is concerned? That is one of the main questions. And what we find is that, I'll say a few words about that. What we find is that you can generate giant effective magnetic fields as a result of strain fields on graphene. So this was one of the proposals by Castroneto, which appeared in PRL. Sorry I didn't put the reference for it, but if somebody needs it, I can give it to you later. So what the proposal was that if you have this graphene sheet and you make these different patterns on the substrate and place the graphene sheet on top of this substrate, it might lead to in different ways. I mean, these are just a sort of a proposal that you can have all these different kind of things happening. It doesn't have to be all at the same time on the same substrate. What that does is actually causes a certain region of graphene to be strained, locally strained. What local strain means is, if you look at, in the literature, that HAB is usually represented as a T, and Ri is the position of the lattice site, and N is the position vector of the neighboring lattice sites. So what you're talking about strain, if you mathematically want to represent strain, what you're saying is that you are changing it by a small amount. And if you go through the mathematics, which is not very difficult, it's given in the Reviews of Modern Physics paper that is probably on the website also. And you can represent the Hamiltonian in terms of a potential, a gauge potential, which is, or an effective potential, which is related to this deformation of the hopping amplitude delta. So in a sense, what you get is that the Hamiltonian of the system becomes the Hamiltonian of the electrons in a magnetic field. But this it's not really a magnetic field from external magnetic. It's not an external magnetic field. It's a magnetic field that arises because of the deformation of the graphene sheet locally, or because of the strain fields. And there was also another proposal which appeared in Nature Physics last year by Ganaim, and Gaim, where they showed that if you engineer strain along certain crystallographic directions, you can also induce a uniform magnetic field perpendicular to the sheet. And so this is like, stretching graphene in a certain direction, this in this direction, in this direction, this direction. How it's going to be accomplished, I mean, that's a question that we will address in a moment. But they were able to show that and they did some numerical calculation that they showed that this does lead to uniform magnetic fields, and they determine the density of states, which shows these oscillations when you change the gate voltage, and which is a sign of the magnetic field effect. So now I'm going to, lastly what I'm going to talk about is the realization of this. So an interesting paper came out last year where they were able to do all this, in the sense that they were able to perform an experiment where they were able to apply strain on graphene, and they determined that the magnetic fields generated are of very high magnitudes. And this is you cannot have a real magnetic field, but this is a magnetic field that is caused by this strain.
One question here. In the matrix element HAB, H is a Hermitian matrix, so you're changing off-diagonal entries by a certain amount. And you're saying this can be rewritten in terms of, since it's a very 2 by 2 matrix, you can rewrite this in terms of the polymatrices and with some coefficient, and that coefficient is the gauge field. But gauge field isn't gauge field more than that, because I can change, there's a gauge transformation that I can do. So is that visible here or not?
No, it's not. They just call it an effective gauge field, but there is no. It's not. It doesn't obey the gauge transformation.
A transverse magnetic field. It's producing a real transverse magnetic field.
It is just producing a real transverse magnetic field. Yes.
So, how do you explain that? There must be a gauge potential then.
A is the gauge potential that arises from the deformation.
But it doesn't have gauge. The gauge transformation is not.
I have not seen it discussed in the literature, but I'm not sure. I'll have to check and come back to you on that.
So this is a real measurable magnetic field.
Yes.
Some kind of magnetometer here. You will measure 300 Tesla.
The thing is that you can determine what the magnetic field is by doing a scanning tunneling microscopy type measurement of the local density of states.
A magnetic force microscopy measurement. If you do a magnetic force microscopy with this engineered strain.
But what I'm going to talk about right now is they're doing in scanning tunneling spectroscopy. So what they're doing is they're looking at the local density of state at a certain local constrained region of graphene. And what they find is that if you look at the local density of states and you plot that local density of states, it gives signatures of or gives you the same kind of a result that you would get for a magnetic field of a certain strength. And because what they do is they write the magnetic. Let me just tell you what they've done. So what they have is, in this experiment, what they've done is they have a graphene sheet. First, what they've looked at is they have a platinum surface, and they place ethylene on it, and then they need this this surface, and a graphene is left on that sheet. And once they have this graphene sheet, then they cool this whole sample, and because of the difference in the thermal coefficients of platinum and graphene, you get these small regions where it is you get these what they call nanobubbles. These are these strain regions, and these strain regions you can see these 1, 2, 3, 4, 5 nanobubbles, and this is some part of the graphene sheet with the hexagonal structure, and these are some ethylene atoms, molecules which have sitting on the platinum surface. This is the platinum surface, this is the graphene sheet, and these nano bubble region. And what they do is a scanning tunneling spectroscopy type measurement of the local density of states in this region. And what they find is they look at the differential conductance, and what they find is that they find these peaks, because the differential conductance actually tells you about the local density of states, and there are peaks in the local density of states, and this corresponds to the n is equal to 0 level, this corresponds to the n is equal to 1 peak, this then is equal to 2 peaks. So the question now arises that whether these are due to the magnetic field or arising due to the strained magnetic field, or it is something else. So what they do is they plot this dispersion, they plot the energy eigenvalues and see the trend that it follows, and they find that it fits pretty well with the square root of n case, which was, if you remember, for the Landau levels in graphene, they go as square root of n. So they have sort of like looked at different scenarios in the sense there could be defects that are causing it, but they rule that out, and they look at some other things that could be there. So, and they built up a model for how strong this magnetic field is, and that is in terms of the height of the bubble, the length of the bubble, and the change in the hopping amplitude with respect to that response. And they predicted 300%. So that's it for the third lecture. Questions? I mean, that was what I was trying to explain, that even these strain fields, I mean, if you strain graphene sheet, the potential, vector potential appears in the Dirac Hamiltonian, and that, in a sense, acts as that represents a magnetic field. So all the properties of magnetic field effects you would see in strain graphene. Unless you apply strain, without applying strain, you won't have this. So the strain can be related to a vector potential, and so the Hamiltonian is essentially the Dirac Hamiltonian in the magnetic.
A fractional Hall effect, quantum Hall effect observed in graphene in 2009. But what was the initial material in which this phenomenon was observed?
You're not talking about graphene. Earlier than graphene, the original one?
Yeah.
Was gallium arsenide, aluminum gallium arsenide heterostructures. That was the experiment done by Stromer and Sui. So that is semiconductor heterostructures. Two gates.
Any more questions? Alright, let's thank the speaker. Just a couple of announcements. We are going to break for lunch now.